Hello everyone and welcome to Vector Visual Timing Day. From experience we know that multi-core systems can be unpredictable, and upon small changes the impact in timing and data flow cannot be easily determined. Investigating into this field, a few years ago we came across the approach of logical execution time, or LET, that helps to make the multi-core systems deterministic. I am Arlinda Almazi and I'm a solution manager for timing at Embedded Software and Systems Department at Vector. I'm here to present you the logical execution time paradigm that will mask the timing jitter and make your systems more deterministic. You will learn today how to realize the LET in microsar classic-based projects and as such make your systems more robust. So let's dig into it. I have a small hint how to recall LET even beyond this presentation. Well, think about Tom and Jerry. As children in the past, we enjoyed to watch every episode of it while Tom was chasing Jerry because we knew at the beginning of every episode that regardless what happens, Tom will never succeed and eat Jerry. The producers gave us very deterministic outcomes at predefined point in times, and as such, we could enjoy the journey that was ahead of us. Now, let's take this pattern into mind and come back to our adulthood, where we are talking about multi-core systems, tasks, and LET. To illustrate the motivation of the LET, let's work with a simple multi-core system having 2 cores and several tasks executing on them. We know that every instance of the task might take different execution times. And from real-time perspective, we will define our event chain as the task sequence of task dependencies among them. Particularly talking, the output of task A is going to be consumed by task B, and the output of task B is going to be consumed by task C. Since the execution time of the different tasks instances is varying, we also can see that the end-to-end latency for our defined event chain is also showing variations. In this kind of situations, for predictability, we normally are talking about timing values in the ranges of minimum, maximum, and average observed timing values. An additional parameter that we need to take into consideration is the data consistency. Here, we need a dedicated mechanisms in order to ensure it. Now, let's analyze what would be the behavior if we have a small change in our system. Let's say the developer is changing the implementation of one runnable which is executing in task B. For any reason now, this runnable is taking longer time than before. What happens to the timing and data flow here? Let's analyze. So initially, we immediately see that we have a different values regarding minimum and maximum latencies here. When it comes to the data flow, we can observe now that the order of them also changed. In this particular case, the task C, instance 0, is now not consuming the outputs of the task B, but taking any initial or default values here. Same behavior it is in this event chain where this is not consuming the outputs of this instance of task B, but instead is taking the second instance of it, so we have a longer event chain here. What we can realize is that in this kind of typical systems where bounded execution time is applied, timing behavior, especially upon updates, the event chain is not, the causal order of the event chains is not guaranteed. We cannot talk immediately about time determinism. To a certain degree, it can be perhaps predicted, but we don't have a deterministic timing behavior. As such, upon those changes, as we saw, we cannot predict the impact of it. Therefore, we would need to retest the system to see if it is schedulable and if the timeline is verified. And maybe it can be the case that there are changes that are needed in the design and in the integration to be done. So the question remains, how can we achieve time and data flow determinism? Well, we said that the solution for it, we see it the logical execution time paradigm. So what is LET in essence? LET is a paradigm that assumes the software is made of concurrent runnables that are running periodically. These runnables have a well-defined data dependencies between them, and it fixes the points in time when this data exchange between runnables is taking. So we have a fixed time point when runnables are reading their inputs and when exactly those runnables are writing their outputs. It is focusing on the points in time when the data is transferred without making any assumption or concrete specification about the time when data is processed. Within this interval, the data should be processed and can be interrupted, can run in faster or lower core, or even terminate the processing before the time defined for the right outputs. But even though it is terminating before, the outputs will be made available only at specific points in time. As such, LET is applied for implicit sender-receiver communications in AUTOSAR, and it is already specified and standardized in the AUTOSAR standard. In the classical part, we can see it already available from release 19 in the timing extension documents. Let's see now in our example how LET is bringing the time and data flow determinism that we were aiming for. Going back to the example that we saw initially, we transform very simply that each task, it becomes a specific LET interval, and we have in the beginning the read of the inputs, and in the end of the interval, the termination or the writing of the outputs. Those intervals, they stay fixed and the same for all instances of the different tasks, or in this case, our LET intervals. Since we have fixed intervals, we can see that from the end-to-end latency, in comparison to the before case, we are talking now about very deterministic timing values, because regardless on the execution time of different instances of the task, we have those LET intervals and the times when data is exchanged fixed and stable. Applying the same assumption that what happens now if a certain runnable is changed and is taking more execution time as before. We can see that from timing perspective, pretty much nothing changed. Especially so looking at the end-to-end latencies, the timing since the timing intervals windows did not change, we have the same end-to-end latencies. This is the case, so as long as the runnables or the execution time fits the predefined timing window, we're happy to go and nothing changed in our timing behavior. LET is not a big magic that comes just as that for free. So the determinism and the predictability that we are talking comes at the price of having, in general, higher average end-to-end latencies. This is due to the buffer on time that we are living in those timing interval windows. Also, we can see that at the boundaries of the LET intervals, there can be a CPU load increase. To work around over this, you can change the design of the LET intervals, their duration, and the scheduling of the LET intervals. Another aspect which we cannot ignore are the increased memory requirements for storing those buffers till when the data is terminated and when the processing it is terminated. Here, the research community is already investigating into finding a better optimization regarding buffering and different strategies. And lastly, LET as paradigm comes with the need of having more tool support for the design of the LET intervals, how to map the runnables to the specific intervals, their integration of the highly interconnected systems. But let's not forget the motivation and the benefits that LET was bringing to us. We immediately saw that there is a time determinism for end-to-end timing by eliminating or masking the task jitter. Data flow determinism is also reached with the LET. So the runnables now, they consume input data from known instances, and this is from the design phase. Data stability and data consistency is already by default included with the LET because we are talking about implicit sender-receiver communication. Also, we saw that upon small software updates, the system is robust towards the updates there. And we have platform independence. It can be integrated in different cores from their processing point of view. Lastly, LET is not necessarily anything new, and it is already in the road. In this paper, Mercedes-Benz is already reporting their integration of LET for their multi-core systems. They report that they were able to ensure data determinism, better load balancing, and have their causal event chains implemented and ensured by design. LET, as mentioned, was just paradigm. Now it requires special design, software and hardware mechanisms in order to reach and ensure its semantic. This would be an overview of the path to realize LET. In this session, we will concentrate mainly at the realization part, speaking at the points that are marked in red. Let's get into the details of those. For setting the base for our realization of the LET, we assume that the LET intervals, it is defined. So what are the LET intervals, the runnables map to it, and the critical event chains. More on this you can find in our LET guidelines. After the design of the LET intervals is there, it is important to define also the data flow of the LET intervals. This can be done through the offset timing constraint, where we can then analyze the data flow and plot the sequence of the expected LET intervals. To document the LET intervals and the timing constraints, the Timex of AUTOSAR standard is providing us the means for it. An LET interval can be defined with event chains, and their properties, so duration, period, and offset, can be determined through the timing constraints of reaction latency, period, and offset. Once we have all of this as a base, let's see at the integration of LET in microsar classic systems. First of all, we need a dedicated buffering approach in order to handle the LET semantic. For this reason, microsar RTE is already providing an RTE add-on with log-based buffering protocol. For each LET interval, RTE is automatically creating two schedulable entities, one in the beginning, so the release, and the one at the terminate of the LET interval. These schedulable entities are taking care about preserving the buffers, the local buffers for preserving the LET semantic, and are generated automatically by RTE. Once the definition is done, which LET interval, respectively, which software component is running in which core, we can continue with the LET scheduling. We will illustrate here only how the mapping or integration of the LET intervals in core 0 is done. First, we have to consider several aspects in order to preserve the semantic. Initially, so we need to isolate and guarantee that those local buffers or scheduling entities are executed and are not preempted, and they are executed at the right point in times. So to do that, we will use a dedicated tasks, called here LET task release and LET task terminate, make them basic and non-preemptive, and assign the highest priority so that they are ensured their execution and allocation to the cores. For the LET interval, the release schedulable entity will be mapped at the release task, and the corresponding terminate of the LET interval 1 will be mapped at the task terminate here. To ensure the right timing or the distance in the LET interval, we will use the activation offset parameter. Please note here that even though we're talking about offset value the same here, the activation offset here is referring to the runnable to task mapping parameter, while this offset is a timing constraint defined in Timex. The same approach we are doing for the schedulable entities of the other LET intervals, and so on. This next point is we need to ensure also the right activation of computation runnables, meaning the runnables that were assigned to the LET intervals. For this one, we will map those runnables to a dedicated task, and this can be preempted fully, and it is of a type basic task. To ensure the right activation, timing activation of the LET intervals, RTE is automatically generating a schedule table and the corresponding expiry points based on our mappings. We can see that the release and computation are activated at the same time, and later on, based on the activation offset configured, the next expiry point for the termination is automatically configured. Once having this, let's say we continue with the next steps of normal development. We generate the code, we continue with the flashing the system in the target, and so on. And what we are interested next is to verify and monitor how the LET's design that we have done and configured, it is really realized, and can we derive out of it any optimizations. We provide here two possibilities, the LET monitoring and LET verification. Through recorded scheduling traces, which will be covered in many more details in several sessions in this event, we import the scheduling traces so that we can analyze what happened in the system and when those LET intervals are executed. By importing the trace in the TA tool suite, we can see the LET intervals as dedicated objects. As such, then we can see the occurrences of the LET intervals, when exactly the schedulable entities, so the release and terminate, really took place, if the order of those runnables, so release, compute, and terminate, is as expected, and many metrics that shows the timing behavior or are the key performance indicators for the LET behavior there. Based on the outcomes here, we can use this data and improve our design and iterate it again through the whole steps in order to achieve an optimal design of the LET. If this is not sufficient, if you want to know more and observe the behavior of the LET even when the system is being tested, we have the possibility of using the LET monitoring through RTM measurements. In this case, you can observe what are the typical behaviors of the execution times of the different runnables mapped into the LET intervals. What is the space remaining there for adding further functionalities? And in case there is a violation of the LET semantic detected, a dedicated callback can be invoked and the system can behave in a specified way. And with that, I would like to conclude the presentation for today. What we learned is that the logical execution time, or LET paradigm, guarantees us the time and data flow determinism in multi-core systems. We have a methodological design and development of LET application in an ecosystem of different toolings: TA Tool Suite, DaVinci Configurator, Classic, MicroSAR Classic RTE, Canoe, runtime measurements, and so on. And if you want to have more detailed information about the individual steps from the design till the verification of the LET monitoring, we have the LET guidelines going into the depths of this part. Thank you, and I look forward to your questions.